So I want to talk about the hydrogen atom, in particular line spectra that come across with it. What you may be asking yourself is, what is a line spectrum? And I'll show you over here. A line spectra is what we see when we excite hydrogen. Okay, we excite hydrogen, and then we look at what light is coming out of that spectrum. And how that works is actually pretty simple. We pass a current through through a sample of hydrogen gas, and then what we are ending up with, if you look at it this way, all right, you have a sample of hydrogen gas that gets excited, right? So here's the sample of hydrogen gas over here. That gets excited, it passes through a slit. As it goes through the slit, it hits a prism, and that light gets spread out. So the light gets spread out into the different wavelengths that are comprising of the light that's coming out of this pink tube. And what it is, it's a combination of various different colors of light that our eyes are perceiving. So as this comes through, it gets split, and we end up seeing a line spectrum. And what that is that various different lines have been split out by the prism in the light coming from the hydrogen sample. And each one of these lines, because they're colored, we know each one of these lines has a specific wavelength. Let's go a little lower. I'll hold it right here. We can see that one is at 400 nanometers, or just about 400 nanometers, and there's another one that's around 450 nanometers as well. One that's closer to 500, that's at the other lighter blue. And there's one red line that's down there about 650. Now, each one of these is representing specific amounts of energy being absorbed by electrons. So this is what Niels Bohr observed when he excited hydrogen gas and looked at the line spectrum. So let's take a look at what exactly is happening here. All right, we'll leave that up there for the time being. All right. And we can't see anything because of the light coming off the screen. So, let me fix that. All right, so what exactly is happening here is that an electron is being excited. New room, new problems. An electron is being excited when it gets hit by light, or in this case, energy associated with light. That's the electric current that's going through the hydrogen sample. So one electron that's here in the ground state, so the closest state to the nucleus, where it normally is. So this is the ground state. The electron gets promoted, and a lot of energy goes into it. So the electron ends up absorbing that energy and shooting up to an outer level. Now, as this electron begins to decay, we see different different amounts of light that are coming from it. So if an electron comes up here, the first place it decays to is the second orbital. So this is 1, and this is 2. As that electron decays, decays just means it loses some energy. So the electron jumps from this point to that point, and what we end up seeing is a large amount of energy, because what I've gone from is this 2, 3, 4, 5, 6. So that's 6. This goes from 6 to 2. And you can see the distance there. That's a large amount of energy that's being shed by this electron. Okay? So a lot of energy comes out going from 6 to 2. And the light that we end up seeing from that is the purple light, if I'm not mistaken. Let's see. Going from 6 to 2, yep. 6 to 2, we end up seeing the purple light. And the purple light, remember, the more it goes towards blue, the more energetic that light is. So if I'm seeing purple light, it's a big energy difference. That means there's a lot of energy in that particular photon. So this is the purple visible light. Yeah, I actually got purple here, so I'll use it. Okay, so that goes from level 6 to 2. Right? So it shoots off a lot of energy. If I do something that is not so energetic, say I go from here, which is level 3, okay, and I go to level 2, Wow. Dead pen. How about that? Level 3. This goes to level 2. And that's just the electron going from one orbit to a lower orbit. That goes from level 3 to level 2. And what that's going to do is shoot off some other colored light. But notice that there's not a lot of energy that's coming from this location. So the light that comes out of here is red, because red is not very energetic light. All right? Now you want to look at this and you say, all right, so we've got circles, we've got things that are decaying, we've got different types of light that are being shut off here. Is there a better way of looking at this? An easier way? Sure. All right? Think about it this way. Okay, you're in a large, fancy hotel that's very, very thin. Okay, and you start off here on the first floor. There's an elevator here. Okay, think about the amount of energy that it takes to move the elevator from one level to the next. Okay, the more energy it takes to move between those levels, as I've got to put more energy into that elevator, right? So as I move up in these floors, so I go to second, or third, or fourth, fifth, or sixth, or seventh, as we move up in our elevator, we are expending more energy to get that elevator to a higher distance, right? It's the idea of potential energy. More energy is stored to push the elevator up to a higher floor. Okay? And also we're losing that energy when the elevator drops to the bottom floor. Okay? Same general idea in quantum physics when we're talking about energy emission by light. If I go from 6th floor to 2nd floor, I have to shed that much energy. So you can see that it's a lot of energy. And the light that's coming out of here has got to be that purple light that we saw before. Okay? Now, if you are observant, okay, and you can look at my art and say, that art's not very good. Congratulations, you're beginning to be an art critic. But if you notice, the way I try to draw this is that every single ring that we get out here, each one of these gaps is getting smaller. Okay? And why are those gaps getting smaller? Well, if you think about that electron around that hydrogen nucleus, the only thing in the hydrogen nucleus is a proton. Okay, so let me erase my building here. So if I look at my nucleus, and I've got, let's grab the dip pen again, and I've got myself a proton here, and it's got a positive charge. The electron that is orbiting it, okay, has its own negative charge. They're sort of attracted to that positive charge, and this reaches a certain ground state, a certain well of energy, okay, where it likes to be. So it's what we call a ground state. And what I'm going to do is I'm going to represent this using a graph, because scientists like graphs, right? Okay, so this is distance from our proton, okay? And it's the distance of the electron from that proton. This over here, this is going to be energy. Now, if we look at where that electron is and how much energy it's going to expend trying to move, so here's the electron, and I'll call this the ground state, because there's a certain amount of energy that's stuck inside that electron for it to be moving around. So there's a certain amount of energy that's in there. So this is E, and this is the ground state. And we're going to call this the first floor. N is equal to 1. All right? We've also noticed that as we start pumping energy into this, we're starting to see some energy being shot out. And at that point, we're going to get to here, and this is going to be the point where my N is equal to 2. Okay? If I get to N equals 3, and it's a little less than this gap. So this gap is a little less than that gap. The biggest gap is between 1 and 2. The next biggest gap is between 2 and 3. What's the next biggest gap? You said 3 to 4, go get yourself a cookie, right? All right, so 3 to 4 is here. So here n is equal to 4, all right? And then n at this point is equal to 5. Okay? Now I'm going to erase these a little bit, and I'm going to show you just a little bit of what this curve actually looks like. So remember these numbers. All right? And I'm going to use green for this. And I'm going to show you what this looks like. And what's going on there. So here's n is equal to 1. Here n is equal to 2. N is equal to 3. N is equal to 4. And if you notice, n equal to 5 is right there. And then n is equal to 6. And n is equal to 7. Then at a certain point, the space between each one of those levels is getting smaller and smaller. Now, why is that level, the area getting smaller and smaller? Okay? Have you thought about it? Go ahead and pause it and think about it. All right, good. The reason that this is getting smaller is, in fact, that it's getting further away from the proton. The attractive force between the proton and the electron only works to a certain distance, at which point, after a while, that electron just sort of flattens out and it becomes a free electron. The electron's gone, it's not coming back. The photoelectric effect. You hit a metal with light, some electrons bounce out because they've been excited beyond the scope of which they're being held. Okay? All right. There's one other thing about this graph that I do want to show, is that this is the ground state. Okay? Whenever we have a well, there's got to be two sides to the well. What happens over here? Aha! Well, at that point, if we start moving the electron closer to the proton, the energy that's got to go up for us to force that electron towards that proton. Until a certain point where the two meet, the electron gets captured, and the proton neutralizes to become a neutron. And where does that happen? At neutron stars. Of course, everybody knows that. Okay, so just to give you an idea, a collapsed star of giant mass and high gravity is the only thing that could really force this to happen. It's supposed to happen in black holes as well, but we haven't examined a black hole. We just know that they exist, and there's a lot of math that goes in behind that. Okay, but for our case, for everything that we're doing in chemistry, the quantum states Bohr's model deals with the electrons being pushed to a certain level. And this is what quantum is all about. There's a certain amount of energy, a small quantum of energy, that's required to move an electron from one shell to another. Okay, there's not a gradual progression of that electron moving from one level to another. The electron has to be displaced by specific quantized amounts, and quantum just means a set amount, a specific quanta of energy. Okay? I can only move the electron from 2 to 3 if it absorbs the amount of energy required to move it from 2 to 3. Okay? So a specific wavelength of light is going to be the only thing that moves the electron from level 2 to level 3. A specific amount of energy is going to move 2 to 4 and 2 to 5. All right? It's not a ramping process. It's a specific amount of energy. Okay? If I use half the energy to go from 2 to 3, the electron's not going to go to point 2.5. Nothing's going to happen. The electron's going to ignore it until it hits that magic spot that pushes the electron from 2 to 3. That's the quantum amount. Now let's look at the math that's associated with this.